Okay, let's talk a little bit about batteries and other types of electrochemical cells, particularly some of those that might be available commercially. Many cells that are available commercially are what we call primary voltaic cells, and those are pretty much the ones we've talked about so far. They generally cannot be recharged once the cell has been discharged. That is, when you have a dead battery, you can't recharge it. We know these days we do have rechargeable cells, some with varying capacities of recharge. Some do better than others. Dry cells, a lot of times we have a zinc cap where we have our basic zinc oxidation being the anode, and the cathode is manganese dioxide, ammonium chloride, and a graphite paste, where the ammonium ion is reduced to ammonia and a little hydrogen. There's usually a vent for the gas to escape, and since the gas escapes, it's not going to be strictly reversible. So the overall reaction is zinc reacting with the ammonium ion to produce zinc 2 plus, ammonia, and hydrogen gas, 1.6 volt cell potential. You put a load on it, it's going to drop slightly, and they'll give us 1.5 as we're used to seeing on a lot of cells. The graphite rod serves as an inert cathode. There's usually a zinc skin producing the anode. As hydrogen gas is produced, it's oxidized by the manganese oxide, prevents collection of H2 on the cathode, which would stop the reaction once you have a lot of hydrogen adsorbed onto the electrode. But there usually is a vent for it to escape should it get there. So the H2 reacting with the manganese dioxide produces an MnOOH. The dry battery can often look like this. You got the zinc on the outside of the battery, the paste in the middle. There's usually a separator to keep those two apart. But it's porous, allowing ions to transfer to keep the electrical charge flowing. The graphite electrodes into the middle. It touches the zinc. It touches the paste. And electrons do transfer via that external circuit that's not in the solution. And you have a wrapper to keep all that contained. And so that's generally what happens. And that's the basic idea. The anode being the zinc skin, the cathode being the graphite rod, and electrical conduction between the two via the top. An alkaline battery, the ammonium chloride is replaced with potassium hydroxide, but it's a very similar type construction. Zinc reacting with hydroxide will produce a zinc hydroxide instead of just straight zinc plus 2, but you still get the 2 electrons. The cathode is the reduction in manganese dioxide. Advantage, you don't get the gas formation that you have to worry about. Manganese dioxide reacts with water, 2 electrons to produce the MnOOH that you would have gotten out of the other cell, and some hydroxide. Back again where hydroxide's more or less acting as a catalyst because you use 2 and you get 2 back. The cell produces about 1.5 volts, so slightly less than the dry cell, but the alkaline battery dominates the market. We're in a lot of your AA, AAA type batteries, that's what's going on. This is more of your watch style flat battery, but you can see that potassium hydroxide saturated with zinc oxide in the absorbent material. There's again a zinc anode, and you still got some mercury oxide with graphite in the electrode and a steel inner case. And there is a gas vent in this one for just in case. Secondary voltaic cells or reversible cells can be recharged by passing electricity we supply through the battery in the opposite direction as the normal flow, allowing it to recharge and be reused. One of the classic batteries is the lead acid battery, or quote-unquote car battery. Usually consists of 6 anode cathode pairs, each producing about 2 volts for a 12-volt total voltage. You can have higher voltages, particularly for heavy equipment or larger heavy-duty trucks, but you'd need more cathode-anode pairs. Essentially, the cathode is lead oxide on a metal grid and sulfuric acid. And so you get lead oxide reacting with sulfate and 4 acids, plus 2 electrons to produce lead sulfate, which does precipitate out onto the electrode and 2 waters. The anode is just lead metal, which reacts with the sulfate to produce lead sulfate and 2 electrons, which also precipitates out onto the other electrode, so you're getting precipitation of lead sulfate on both electrodes. So lead oxide plus lead plus 2 sulfates plus 4 hydrogens produces 2 lead sulfates and 2 waters, which is the overall reaction. And so the cathode reaction of the lead oxide is a positive 1.685 volts, and for the anode, which is the lead metal, a negative 0.356 volts, giving you just over 12 volts of voltage per cell. But again, if you put load on a cell, the voltage will drop just a bit, giving you about 12 volts on the battery. And it depends on how much load and what the resistance is, and there's a lot of factors, but the voltage does tend to drop once you put a load on the battery. This is the straight load on the battery with just, say, a voltage meter attached, which has minimal resistance. Usually they'll use wood or glass spacing fibers. You use that fiberglass is probably common in today's batteries. Prevent the electrodes from touching, which would short out your cell. And you can see a diagram that indicates that. And you can see the multiple cells, multiple anode cathode pairs, but then you do ultimately get 2 electrodes that do rise out of the battery for you to connect to. But the whole thing is submerged in the same sulfuric acid solution. The liquid can evaporate over time, so you do see some batteries where you can add water. It's usually not terribly recommended because of safety reasons. But if you do have a concentrated sulfuric acid there, you could dilute it back to the normal with some water. It's not going to add any acid or sulfate though. It just, if some of it evaporates, you could make up for it with that water. Nickel cadmium batteries are also popular because they can be recharged. Cadmium and 2 hydroxides forms the cadmium hydroxide and 2 electrons. The cathode reduction of the nickel 4 oxide. Notice this is not nickel 2, which is the overall common isotope. Nickel 2 is so common that a lot of people don't use the Roman numeral with Roman numeral 2 with nickel 2, but you can have other oxidation states of nickel. They're just not overly common. And so this is a nickel 4 oxide reacting with water, 2 electrons forming nickel hydroxide and 2 hydroxides. That would be the cathode, where the anode is the oxidation of the cadmium metal. And so we call it NiCad for nickel and cadmium. Overall reaction would be the cadmium reacting with nickel oxide and water to produce the cadmium hydroxide and nickel hydroxide, both of which will precipitate 1.4 volts per cell, but it is very rechargeable. Running current across it, in the lead acid battery, that's why you have an alternator. You run the electricity across the battery while the gasoline engine's running. In the case of an NiCad, you're going to put it on a charger where you use normal electricity from the power company to charge the cell. A lot of cordless tools use NiCad batteries. one cell, the hydrogen oxygen fuel cell, while not strictly a battery, the fuel cells have reactants that are continuously supplied and products are continuously removed to keep the reaction going. But you're focused on that oxidation of the hydrogen to produce the electricity. But you want to do it in a more controlled way than burning it, which would be bad. Cathode's the reduction of the oxygen. Both reactions have water associated with them. You produce water in the hydrogen reaction, use it in the water reaction, and you see that you get the hydroxide back from the oxygen reaction, which you use in the hydrogen reaction. So it's a good complete circuit as long as you can keep that going. So the net reaction would just be the same as burning of the oxygen or hydrogen in the presence of oxygen. And you can see this on a little bit more cartoony scale, but you are going to produce voltage. You can get a lot of horsepower out of a hydrogen power fuel cell, say in a car. And you don't per se have to memorize these reactions if you're taking my class, but I want you to be familiar with the hydrogen power fuel cells design. You do use a graphite plus a catalyst to make this lower the energy threshold, inletting it and causing that to produce electricity. And it can work rather well. Problem is the hydrogen is very flammable, and so this really hasn't reached the consumer level like I thought it might have in some years gone by. I thought, oh, this hydrogen power fuel cell is going to really catch on. And about 10 or 15 years has passed since I originally thought that, and it hasn't really caught on. And you do have some risk with the general public working with hydrogen gas. And that's probably why it didn't catch on like some people thought that it might. Because a lot of people, including Nobel laureates, I've heard say that, oh, this is going to catch on. I really think it's going to catch on. And it really didn't catch on to the extent that anybody really predicted that it would. And it's just, my thought is just it's a general hazard in working with hydrogen because you have to inlet that hydrogen and it has to be done in a safe way. And the untrained person is likely not going to be able to do that in a way that's going to be significantly safe. They're going to have to make that transition a lot more safe for the general public to be able to do it safely before it really catches on. But I think ultimately it will still catch on because it's probably the cleanest energy out there once you get past initial construction. Corrosion is sort of an application because metals will oxidize, particularly if they get wet and are left exposed to the air, like iron. You can avoid corrosion by painting it, which just means that you keep the metal away from the air so it can't oxidize, or you can galvanize it with a thin layer of zinc. As long as zinc is a more active metal than the one you're trying to protect, which it is in the case of iron, you essentially have a sacrificial zinc anode that allows the iron to stay in a reduced form. And so it protects it for quite a while. So the zinc reduction versus the iron reduction, you see the zinc is more negative, meaning it would rather be oxidized relative to the iron. So it would work as a protection for the iron. And so the zinc is preferentially oxidized where the iron stays in the reduced form, protecting the structure that has, say, the nail in it or whatever the iron structure is. So if we look, it's easier to oxidize, and so we use a sacrificial zinc anode, and that's kind of what this picture's the overall process. There you have the rust that forms if it's not protected, and especially if it gets wet, iron will rust, especially if it's salt water. So the iron's being oxidized, the oxygen's being reduced to a hydroxide, and you end up forming iron oxide on the surface. So what you end up with is 2 irons plus 3/2 oxygen plus some number of waters is going to produce a ferric oxide, which is rust, plus some number of waters. But if we galvanize, we have that protective zinc coating, and the zinc oxidation allows the iron to be reduced and stay reduced, even if it gets wet. And that's something we have to keep in mind. You can either paint it and just try to seal it away, but as the paint wears away, the metal begins to rust, or you can use the zinc coating, which tends to work a little better than painting in the long run.